Okay, good. So yeah, I'll change topics a little bit now with my presentation. And as Peter just said, now I'll be talking about controls of the land carbon sink projections. And mainly I'll be focusing on the relevance of soil moisture. So not really an emergent constraint as we've been talking about, but more trying to understand differences in MVP projections of the models towards the end of the century based on intermodal differences in the soil moisture conditions and in the sensitivity of MVP to soil moisture. So now the motivation why we wanted to look at this, or why we wanted to focus on soil moisture as a relevant control of the land carbon sink, is based on this observation study from Humphrey et al., which showed a quite strong sensitivity of the carbon growth rate, of the atmospheric carbon growth rate of MVP to terrestrial water storage. And now in this study, we want to go beyond this global relation and analyze the controls of MVP in space, given that the models actually provide all the necessary information at every grid cell. In this case, we want to distinguish between the controls of the detrended interannual variability and of the trend in MVP. So I want to start with this simple example of an annual time series of MVP in a single grid cell in the Amazon and for a specific model to explain our approach. So basically, if we apply a locally weighted scatterplot smooth algorithm, we can obtain an estimate of the trend in MVP towards the future, shown here in red. And then the detrended interannual variability can be estimated here in red also, can be estimated by taking the difference between the annual time series minus the trend series. So now that I've separated the interannual variability and the trend in MVP, I can do the same with the time series of annual time series of air temperature and of soil moisture, which are the two controls that I'm considering here as relevant for explaining MVP in the models. Now, when we use a simple stepwise linear regression with no interaction terms to explain MVP as a function only of temperature and soil moisture, we can see that for this particularly grid cell in the Amazon, temperature and soil moisture explain really well the interannual variability in MVP, and a little bit less well the trend, although the R-square is still relatively high, 0.6 here. Now in the following, I will focus on the controls of the detrended interannual variability in MVP first. So what I showed before was the example for a specific grid cell and a specific model. So now we can also apply this regression at each grid cell, but for all grid cells in the world and for all CMIP6 models. And what I'm showing in these maps is the sign of the coefficient B in the regression, the coefficient for the temperature and for the soil moisture control. So basically what these maps are showing are that, for example, in the case of temperature, we have a negative value of the coefficient, indicating that generally years where we have higher temperature will correspond to years where you have lower MVP, except on the higher latitudes where the opposite is true. Whereas for the case of soil moisture, you generally have a positive coefficient, indicating that years with lower soil moisture will also have lower MVP in general. Now, these next maps show the R-square between the interannual variability in MVP time series and the regression estimate using both temperature and soil moisture. Now, these plots to the right here are a summary of these maps and basically show the distribution of the R-square values. And we can see already that both temperature and soil moisture can help explain quite a bit of the interannual variability in MVP. Now, if we apply the same method, but if we only use the soil moisture as the only explanatory variable of the interannual variability, we obtain these R-square values here shown in purple. And if we do the same for temperature, we obtain only for temperature as an explanatory variable, we will obtain the orange bars shown here. Now we see that the purple values of R-square are generally higher than those from temperature only, so we can conclude that soil moisture seems to control more the interannual variability in MVP than what temperature does. So now we can move from the interannual variability explanation to seeing how these controls can explain the trend in MVP. So we do this in a similar way. We fit this simple stepwise regression. And then in this case, we have here the values of the coefficients. So here in the case for temperature, we see that there's a regional dependent relation of temperature with MVP, whereas for soil moisture, we still see this general direct relation, meaning that if you have a decreasing trend in soil moisture, it's likely that you will also have a decreasing trend in MVP. Now this plot again is similar to what I've shown before, and basically shows a global distribution of R-square values from these regression estimates, indicating that we are able to explain quite well the trends in MVP through the trends in temperature and soil moisture, as indicated by the gray bars. And the other point we can make here is that when using only soil moisture as an explanatory variable or only temperature as an explanatory variable, the results are actually quite similar. So we can conclude that both trends in temperature and soil moisture explain the trend in MVP rather well. And we can also say that it seems that soil moisture is as relevant as temperature for explaining these trends in MVP. So far I've shown that soil moisture does play a key role in explaining the detrended interannual variability and also the trend in MVP in most of the individual CMIP6 models. So the idea that we had is to look in the next part is how do differences in soil moisture conditions and in the sensitivity of MVP to soil moisture conditions across the CMIP6 ensemble can help explain intermodal differences in MVP projections. So to start, we can start by looking at average MVP projections towards the end of the century from the different CMIP6 models. And here we can already see some differences across some of the models. For example, if we take CESM and tropical regions, we see that the model generally thinks that the land continues to be a sink of CO2. Whereas if we compare that to the UK ESM model, for example, in this case, most of the tropical land appears to be a source of carbon to the atmosphere. Now in the next slide, when explaining differences across models, I will focus only on the 6 models here to the right and not consider the access model because this is the only one that includes also a phosphorus cycle in addition to the nitrogen cycle. And I will also omit the CAN-ESM and IPSL models because these two do not have a nitrogen cycle and therefore do not account for nutrient limitation as well as the other models do. So now this map here is trying to summarize the differences across the models by taking the intermodal standard deviation in MVP. So basically the intermodal standard deviation of the maps I showed before. And here we can already see that the regions where we have most differences across models are the tropical regions again and the boreal forests. Now in the following, I will show you several controls that I considered that could help explain these differences across the models. So the first one is the sensitivity of MVP to increasing atmospheric CO2 concentration. So if we fit a regression of these differences across the models with differences in the sensitivity, we can obtain these R-square values. Now, if these R-square values we multiply with intermodal standard deviation, we can have actually the explained intermodal differences in grams of carbon per meter square per year. Lastly, the number that I will report here to the right is basically indicating the fraction of the explained variability across the models relative to the total variability that we have. So this was the case for the sensitivity of MVP to CO2, but we also looked at how do differences in average conditions of temperature and soil moisture in the models help explain the differences in MVP. And here for temperature, we can see that it's relevant, especially in Central Africa, where it explains quite a bit of the differences across the models. For soil moisture, we see that is also relevant in parts of the Amazon, Africa, and Southeast Australia. And lastly, we see that also the sensitivity of MVP to temperature or soil moisture also is quite relevant to explain differences across the models, and especially in the boreal forest regions. So basically with this, I would like to come to my conclusion slide and just mention once again that in summary, soil moisture appears to play an important role on controlling the interannual variability and also the trend in MVP in most individual CMIP6 models. And that because of this, we also have that differences in soil moisture and in the sensitivity of MVP to soil moisture across models contribute to explain intermodal differences in the MVP projections. So thanks a lot.